Today's topic is predictive performance of our regression model. Okay, so we're going to look at the situation where we're most concerned with the ability of our regression model to make accurate predictions. Okay, so in order to do that, we're going to introduce some metrics for assessing predictive performance and also some strategies to fit models with good predictive performance. Okay, so today we're going to start by, okay, so let me lay out the context first. So we're talking about predictive performance. Of our models. Okay, and so the context is that sometimes the key application is of our model is to do prediction for new data. Okay, so sometimes the key application of a fitted model is to do prediction on new data. And sometimes prediction is more important, can be more important than interpretability. Okay. And is more important interpretability. Okay, so what have we learned so far that's associated with this idea? Well, we've looked at some model selection criteria. So previously, we looked at some criteria. We saw model selection criteria. So this includes things like AIC, BIC, adjusted R squared. And these things are calculated on our fitted model. So we fit the model and then we compute a statistic based on the fitted model. Okay, so let's just remind ourselves of that and then explain how when we prioritize predictive performance, we might want to use a somewhat different metric. Okay, so that are computed on fitted models. Okay, so these include the things we looked at: AIC, BIC, R squared adjusted. Okay, and what do these criteria do? Well, they're calculated on the fitted model, and so they assess, how well the model explains the data that was used to fit it. Okay, so that's the assess the explanatory power of a model on the data used to fit it. Okay, and that's an important point. Data used to fit it because it doesn't take into account what we might see if we were to use the model to do prediction on data that we have not seen before. Okay, on the data used to fit the model. Okay, and so that's a key point here. It's based on the data used to fit the model, and so it doesn't guarantee anything in terms of the generalize it, how well the model can generalize to new data. Okay, to fit, if we were to think of or when we say fit the model, I mean a kind of equivalent term, which is perhaps more often used in machine learning is, or to train the model. Okay, and the reason I introduced that term is because that ties in well with the idea of having a training set and a testing set and validation set. Okay, so we'll talk about those things today. Okay, so now one of the problems of having a model with lots of variables is that we mentioned before is the idea of overfitting. Okay, so overfitting is when we throw in so many variables that we're actually modeling some of the noise. There's actually no predictive power, and that can lead to a very good fit of the data, but not necessarily guarantee good predictive performance on new data. So implicitly, when we talked about these model selection criteria, each of them introduced a way of penalizing, okay, having too many parameters. Okay, so let's remind ourselves of that. So while these criteria incorporate penalty terms, to try to prevent overfitting. Okay, and they also, not only do they try to prevent overfitting, but they also based on principle that we generally prefer simpler explanations for the data if possible. So remember we mentioned Occam's razor in this case. Okay, so while they have these penalty terms, they don't directly assess. So okay, so how is the model going to do when we apply it to new data? They don't. So that doesn't provide a direct mechanism for assessing that. How well the model predicts on new data. Okay, in terms of that performance. So to be specific, when we want to predicting the response variable on new data. Okay, given what? Well, we're going to be given the explanatory variable, so we'll be given the x variables, but we won't have y on the new data. Okay, on new data, given the predictors. Okay, so that's what we mean by predicting the response. We're gonna for some new data, we're going to know the x variables, we won't know the y, and so we want to do prediction. Now, we've already seen formulas for how to do prediction. Okay, so that's why we've seen beforehand that we have prediction intervals and those sort of things. So we know the formula to do it. The question is how accurate are these predictions going to be? Okay, so we've seen these explanatory metrics. Okay, so when we did model selection previously, we focused on these three quantities. So you're quite familiar with these. At that time, I also mentioned that we can also use criteria that directly assess predictive performance. Okay, so we also mentioned metrics like mean square prediction error, such as MSPE, as measures of predictive accuracy. Okay, so we're going to delve into how to use metrics like these. But before I do that, I do want to mention a few metrics that fall into this category of directly assessing how well the model predicts on data that was not used to fit or to train the model. Okay, so then let's back up a moment and talk about these metrics. Okay, so this is a point that relates to what we talked about before. So we're going to delve into things like mean square prediction error in more detail. Okay, so this is the overarching theme. So to assess predictive accuracy directly, accuracy in prediction. So we need, related to accuracy, well, we need measures of error. So how far away are the predictions from the actual values once we get to see those values? Okay, so we need metrics for measuring prediction error. Okay, so specifically, for example, we can list some metrics. So say we have a bunch of observations that we can use to calculate these metrics. So for example, we evaluate this over, let's say we're given m observations, say m observations. Okay, so what do some examples of these metrics look like? Okay, so one of the most natural ones is, considering that when we fit our regression models, we use least squares. And so what does least squares do? Well, by construction, least squares seeks to minimize. Okay, so remember that it's a solution of an optimization problem, which minimizes the sum of squared errors, right, from the model. So that provides a natural criteria which we can extend to use for assessing prediction accuracy. So given that when we fit the regression, we have sought to minimize the sum of squares error, and therefore the mean squared error of the data. So how is that going to perform on new data? Okay, so all right, so metrics. Okay, so first we have examples of these metrics. Okay, so we have mean squared error. Okay, so I can abbreviate that MSE. Okay, so in general, what is mean squared error? So if I have m observations, then it's simply the average squared error. Okay, so what is the error? Well, the error is the actual observation, yi, minus its fitted value, so I'll call that y hat I. Okay, so that's the error for a particular observation, and then we square it, and then we sum them up and take the average. Okay, so that's the mean squared error. Okay, so let's point out here. So this is so yi is the actual value, and y hat I is the prediction. Or equivalently, if we're applying mean squared error, say on the data that we used to fit it, then this would be the fitted value. Okay, so or fitted value, and that'd be the same as mu hat I if calculated on our training data. I should say predicted value. That's a little more precise. So predicted value. So the difference between the actual value and a predicted value. Okay, so that's a general way expressing that. And so mean squared error, of course, it's the only difference between mean squared error and what I've called mean squared prediction error is what we can call the mean squared error, the mean squared prediction error when we're applying this formula on new data that was not used to fit the model. Okay, so let's just add a note here. So this thing, we call it, so this is equivalent, we call this, call it MSPE if the observations were not used to fit the model. So if applied on new data. Okay, so that's just the difference between those terminologies. So there's a question which is, are the yi's based on observed values from which we use to create the model? Okay, so that's why so just to clarify, that's why we distinguish the cases. So if we're calculating mean squared error on the data we use to fit the model, then these y hat i's are the fitted value, or simply the fitted values, and the yi's are the actual values in our data set that we got to use to fit the model. Now, suppose someone then gives you a batch of new data and asks us to predict yi, but doesn't tell us what yi is, then we're gonna predict them, and we won't be able to. Of course, we won't be able to calculate MSP until eventually we get to see what the actual values were. Okay, so for example, we're asked to forecast, say, I don't know, the price of stocks or something that's in the future. So we have a model for doing that. So we make the prediction. And when the actual data comes in, then we can evaluate how well we did. Okay, so that's where we can calculate the mean squared prediction error when the actual observed values, we get to see them usually after the fact. So for prediction point of view, we can view it as a sort of blinded thing. So when we're asked to make the prediction, we assume we don't actually have the value, and then we'll assess it after. When we get to see the value. Okay, so once we have that, then we can calculate this mean squared error on these new data. So that's what we're calling the mean squared prediction error. Okay, and so that's one metric, and then you can also take the square root of that. Okay, so we can take the root mean squared error. Okay, so that's the RMSE. Okay, so all that is just to take the square root of it. Now, reason is, well, remember the mean squared residual, right, is associated is related to this quantity. Not exactly, because you divide by something else here, but the mean squared error the point is the mean squared error is associated with sigma squared, right? So the sigma squared hat is our estimate of the variance of our error terms. Okay, so this is on the scale of sigma squared. So if we take the square root of it, RMSE is measured on the scale of sigma. Okay, so therefore these two are commonly associated with sigma squared and sigma in terms of the error terms in our model. Okay, so this is on the variance scale. This is on the standard deviation scale. Okay, so that's why it makes sense to sometimes consider it on the actual scale of the observations, because the standard deviation of the errors is sigma. Okay, now of course you don't have to use squared. We can also do other things. So you can also do mean, for example, mean absolute error. Okay, so that's we can abbreviate that mean absolute error. So instead of taking the squared errors, we can take the absolute values of the errors and average them. So it would look like this. Okay, so yi minus y hat I absolute value. Okay, so just to say there's various metrics that we can use for assessing how well the model does on predictions. Now, with that in mind, so we're going to suppose we choose a metric. Okay, so just for simplicity, let's say we're going to use mean squared error. Okay, so conceptually, well, how are we going to assess that if we have a lot of data? Okay, so implicitly, the only way we can assess it is if we have some data where we know the answers, but we're not going to use the responses in the fitting of the model. So that gives us a way to estimate how well our model would do on actual data. Okay, so let me give you that framework, which is called which is typical in statistical learning, which is to divide our data set into three parts, or at least conceptualize our data as having three parts. Okay, so ideally, okay, so we have lots of data, and which we can conceptualize having three parts to it. Okay, so let's say here's our data. Okay, and so I'm going to cut this into three pieces. Okay, so ideally we're going to have some data which we're going to fit our model on. Okay, so let's call this the train component. Okay, so what we're going to do okay, so just for the sake of argument, let's say we have, let's say this consists of n observations. Okay, so we can, for example, we can list the responses y1, y2, up to yn. Okay, so we have observations here. Okay, so what we're going to do with the training data is we use this to fit models. And the idea is on the training data, we can fit as many models as we want for the sake of trying to determine the best one. Okay, so we fit lots of models on training data. Okay, so we can fit as many as we like, as we want. Okay, so this is used for model fitting. So if we're doing regression, we use the training data to calculate least squares estimates. We might throw in, for example, different subsets of predictors as we fit models on our training data. So we can do variable selection and compare a bunch of different models with different numbers of predictors. So that's training data. So in this framework, our second, I should actually make this a little bigger so I have room to explain everything. Okay, and so our second piece is what we call the validation sample. Okay, and so again, suppose we have let's have some observations. Okay, let's say we have v number of observations in this batch. Okay, and so just to label them, so then I can talk about. Okay, so let's say there's v observations. I'm gonna label the response. Let's say y. So I use this. So I use distinguishable indices. I'm gonna call y n plus 1 up to y n plus v. Okay, so there's v number of observations. Okay, so what's the purpose of the validation component? Is to we use this to estimate what the mean square prediction error would be. Okay, so we use this to estimate prediction error. And what we're going to do is for every model that we fit on the training data, we can use the validation sample to estimate the prediction error of that model for each fitted model. Okay, so if we have a lot of training data and we have a lot of validation data, then this using the model to predict on the validation data would give us a way to estimate what would be the real world predictive performance of this model. Okay, so validation, we know the answers. Okay, so therefore we can do this sort of assessments. Okay, so this is, so you can think of these two. This is what we have access to when we are to fit the best possible model. Okay, so suppose we have these, and so we can do this sort of estimation of possible prediction error. Now, in the ideal case, so in this conceptualization, the last piece is what we call the test set or the test data. Okay, so let's say, again, for sake of argument, let's say we have t observations here, and then we can label them. Okay, so where we find y sub n plus v plus 1 up to y n plus v plus t. And okay, so the key difference between the validation and test is we're going to assume that we can't use any of this test data. Assume this is data that we will only see in the future. Okay, so we will not be able to assess using the test data until further down the line when whatever phenomenon we're predicting, we actually get to see the values. So let's describe this piece as used at the very end. For the final assessment of the model. Okay, and so by that time, of course, say we're hired to make our best possible predictions for some future phenomena. Okay, so what we have to do at this point is we can only use we're only going to submit one set of predictions. So we're going to choose the best possible model that we can based on train and validation data, and then we're going to submit that model for prediction. And then finally, well, once the data actually comes out, these y values are actually seen, then we can finally find out how well we actually did. So that's the ideal case in this framework for assessing our models. Okay, so for final assessment of our selected model. Okay, and so the difference between here is the validation allows to estimate what the prediction error would be if we were to apply it on new data, and then when we actually apply it to test data in the actual, this will give us an actual measure of our prediction error. Okay, so one of the well-known textbooks says, assume that this test data, even if we were to have it, assume it's locked up in a vault somewhere and we can't use it until we have done all of our work on these two subsets of the data, and then we finally just apply the model and figure out how we actually do on future data. Okay, so let me just put it here in green. So assume we as modelers don't get to see this. Okay, so for the test data, we only have the predictors. We assume we don't get to see any of these observed values. Okay, now let's pick one of these metrics so I can illustrate these concepts. So let's use say mean squared error. Okay, so I can definitely calculate mean squared error based on for each of these components. Okay, so let's relate it to what we just talked about. Okay, so leave that here. So for example, if we were to use, mean squared error as the metric. Okay, so suppose we fit a model, then and we fit a model based on a fitted model we get. We can compute the mean squared errors. Okay, so well, first let's just write them out. So you can have so the mean squared error on our training data would be the average of these guys. So 1 over n yi minus yi hat. Okay, and so likewise we can calculate our mean squared error on the validation. Okay, so there's v of these observations, so 1 over v, and I want to make the notation clear, which is why I gave them different indices. So now I goes from n plus 1 to n plus v yi minus n squared. And then finally we can calculate a mean squared error on our test sample. Once the observations actually come out, we can finally assess how well our model did on this for say a real world prediction task. Okay, so this will be 1 over t. So now the index is n plus v plus 1 up to n plus v plus t, so those are our test sample. Okay, so now I've written these three quantities. Okay, so they're based on this mean squared error formula, simply applied to the corresponding component of the data. So the reason I write it out is that's related to what we talked about down here. Okay, so the mean squared error on the training data, as I sort of alluded to, is very much related to our estimates of the residual variance. Okay, so it's related to sigma squared hat. Okay, so all right. So notice. Okay, so here's a mean squared error on training. Okay, so notice that this is so this since these are the data that we use to actually train the model, this is actually this looks pretty familiar. This is, well, if I don't have the 1 over n, what is this part? Well, this is the mean squared. Sorry, this is sum of squares residual. Okay, so observe this expression is equal to sum of squares residual over n. Okay, so it's not quite the mean square residual, because our mean square residual is our estimate of sigma squared, and we have to account for the number of predictors used to fit the model. Okay, but the two are actually going to be very, very much related. Okay, so and our usual estimate of sigma squared, so estimate sigma squared hat is a scaled version of this quantity. To compensate for a number of predictors. Specifically, we can remember sigma squared hat is sum of squares residual divided by n minus p minus 1. Okay, so remember the reason we did that is because this is what gives us an unbiased estimate. So expectation of this sigma squared hat is sigma squared. Okay, but these quantities are very much related. So that we have an unbiased estimator. Scale version is to compensate. Okay, so that's this expression. So it's unbiased. Okay, so that's the reason I pointed out, because this mean square error in training is actually just a scaled version of sigma squared hat. Okay, so that's why there's a connection between these two metrics. Okay, so that's just a side. Now, what can we say about mean squared error on validation then? Okay, so this is indeed applying the model that we fitted on data that was not used to fit the model. So this is, in some sense, sort of a real-world test. Okay, we're applying the model to predict for these V samples where we have not seen, which the model, when training, have not seen, but we know the values for. So that's why, in a sense, this mean square error validation gives us an estimate of what the prediction error might be in real-world applications. Okay, so therefore, the mean square error validation, so what can we say about this, is that we can consider to be an estimate, consider it as an estimate of what the mean square prediction error would be on new data. Okay, so that's so you think of this as an estimate of what this one would be. Okay, so the difference, of course, is this one we can fiddle with. Okay, so the whole idea is we can fit as many models as we want on the training data, and then we can pick the one, for example, with the lowest validation mean squared error, and then we can hope that the same model will then generalize well when we actually use it on our test data. Okay, so we can use the validation sample to estimate what the MSPE would be for each of these models that we fitted. Okay, so the idea is that it should be a good estimate of this guy. Okay, so over here, mean square error on our test data. Okay, so this part, my flag would still work. Okay, so no, not going to work. Okay, so mean square error on test then is our actual. So this is the actual. Test of prediction. Okay, so since after test prediction, so in our terminology, let's call this the actual mean square prediction error that we would have on our new data. And so we can think of the validation MSE as a way to estimate what the actual test error would be. Okay, so that's the conceptual framework. Okay, so the reason we can think of this as an estimate is because neither of these were used, okay, in the fitting of the model. Okay, so we hope that this can be a good representation of what the actual test error would be. Okay, so let's add that note down here. Okay, so we hope. Okay, so the idea is that this connection exists because MSE on validation and should approximate MSE on test since neither sets were used to fit neither sets of observations used to fit the model. Okay, so that's the idea behind this framework, and why it can be useful then to hold back some of our data from training, so that we can use it to assess how well our model would do in practice. Okay, so that's the framework. So now I want to talk about what can happen when we overfit. Okay, so I'm going to draw a picture which is pretty classic in statistical learning books. Okay, so I'm going to okay, so let me make some space. I'll leave this for a second. I have this graph up here. Okay, so here's a pretty common graph we'll see in discussions of this point of overfitting. Okay, so on the y-axis, we're going to have our whatever metric we chose for prediction error. So, for example, mean square error. Okay, so we're going to put on here the prediction error on the y-axis, okay, according to whichever metric we chose. Here on the x-axis, we're going to put the number of predictors. Okay, and so this is a graph that's used to illustrate why we need to be careful of overfitting. Okay, so in particular, if you have a lot of predictors, dozens or hundreds of them, then this phenomenon can be particularly it can show up quite strongly. Okay, so the idea is, okay, well, if you don't have enough, if not all the relevant predictors are in the model, then of course you would have a high error. Okay, so okay, so for example, actually I should just call this error metric in general, because we want to apply it to, so this is the error metric, for example, mean square error. Okay, and so the question is, well, what happens when you start to put in the relevant predictors? Then the error metric, so whether you're talking about the mean square error on your training data or on your validation data, that will tend to go down as you start to put the relevant predictors in the model. Okay, so to visualize this, okay, so let's call the let's plot a curve for the error metric, for example, mean square error calculated on our training sample. Okay, so what tends to happen is intuitively the error metric is going to go down as you put more predictors, and then at some point it'll probably level off. Sometimes it doesn't. Sometimes you can put in so many predictors that you can almost get the error metric on your training data to approach 0. Okay, so let's call this. So this is the error metric on our training sample. Now, as I discussed, for example, we're using mean square error. This is very much related to our estimate of the error variance, right? Sigma squared hat. So we've seen this kind of idea before. The more we put more predictors into our model, our estimate of sigma squared tends to go down until it reaches a certain point. And in some cases, it can actually get very close to 0. But what we have to be careful of is all of this actually going to be replicable on our validation sample. Okay, so the validation sample is not used to train the model. So what's the error metric going to look like if I now apply the model on the validation sample? So generally, what happens is that when you don't have very many predictors, the performance on the validation sample often track the performance on the trained data fairly well. So the curve might start out like this. Okay, so reason we usually draw the validation curve a little bit higher is because, for example, mean squared error, your estimate of actual sigma squared is a little bit smaller. Okay, because of the n minus p minus 1. So generally might be a little bit higher. But the key idea is that when we're not overfitting, the performance on the train and the validation should be largely similar. Okay, so that's the key idea. Now, if your number of predictors get very large and we actually see overfitting, what's actually going to happen is it's going to hit some point here where up to a certain number of predictors, we might get similar performance on train and validation. But when there's overfitting, what happens is the training mean square error continues to go down, but what happens on the validation sample is you start to see the performance start to suffer. So what can actually happen is when there's overfitting, this curve can actually go back up. Okay, so this is the validation, the error metric. So calculated on the validation sample. Okay, so let's point out those two features here. So there's sort of an optimum here. Okay, so beyond this point, okay, what we see here is what we call overfitting. Okay, because it appears we're getting further decreases in the model mean square error, but in practice, when you actually apply the model to real data, you actually get higher error. Okay, so that suggests that the model was overfitted. We're actually modeling some of the noise and artificially being able to lower this the error metric on our training data. So this is not good. Okay, overfitting means that we think we're going to do well, but then when we try to validate our model, we're actually doing poorly. And then on the other hand, over here, so before we reach the overfitting phase, so in this part, the train, if we're not overfitting, then the train and validation error are similar. Okay, so that's the key takeaway from this classic machine learning or statistical learning graph. Okay, so in words, let me just add a little bit of clarification to make sure we drill the point home. Okay, so point to drill home is, for example, if we're using so if we're using either, let's say, mean square error or the square root of that, so RMSE, as the metric. Okay, so in this case, remember, like we have estimates of sigma. These correspond in their relationship to sigma squared. Okay, and so we're using these metrics and their associated values in the regression model. So which are as related to. So mean squared error is related to sigma squared, and then root mean squared error is related to sigma. Okay, so let's remind you of that point. Okay, and it is significantly different. Okay, so and it is significantly larger on your validation compared to train. that's evidence that we have overfitted our model. Okay, and so we're overfitted. Well, remember the validation MSE or RMSE is meant to help us estimate what it would be on data we don't get to use for this modeling process. Okay, so that suggests that the model will not generalize well to future test data. Okay, and can't expect the model to do well on potential new data. Okay, so let's use the word generalize. That's often used in this context. So the model doesn't generalize well to new data. Okay, so for example, if your training mean squared error is 5, and your validation mean squared error is like 9 or 10, right? Then which one is a better guess of how well you'll do on your test data? Well, it's the validation one, right? So you might guess that your test on the test data you'll probably do as bad as 9 or 10, and you would not be confident that the 5 you got on training data will generalize well to new data. Okay, so that's the key points here. All right, so in practice, how do we carry out a framework like this? Okay, so, well, assume we don't have access to the test data when we do our modeling. Okay, so we're going to have some data, and so according to this framework, we should divide it into some sort of a training sample and a validation sample. All right, so one way to do that is you just randomly allocate, for example, 80% to train and 20% to validation. And if you have a lot of data, that can give you a pretty good assessment of how well your model would do. Okay, so how do we leverage this framework? All right, so the first strategy, as I sort of been alluded to, is simply take your data set and we divide it into, randomly divide into chunks, train and validation, and then that will allow us to fit the model and assess prediction error. Okay, so we fit a whole bunch of models on our training data, and then pick the one with the lowest validation error. So that'd be one possible but simple strategy. Okay, so let's discuss this next. Okay, so how to use the framework? This framework in practice. Okay, so for example, so the simplest way is randomly divide our available data into train and validation. For example, an 80-20 split. For training and validation. Okay, so in other words, 80% gets used for train, and the other 20% gets used for validation. Okay, so I mean, of course, these are just an example of a commonly used type of split, but by no means the only one we can do. Okay, so we randomly divide the data, then we fit as many models as we want on training data, and we can calculate the validation error for each of those models. Now, there's a couple of potential weaknesses of that approach, however, and that is we didn't use we didn't get to use all of our data ever for training because the part that we set aside for validation was never used for any kind of model training. Okay, so let's make a couple notes here. Okay, and then weaknesses of this approach. One is that we never doesn't use all of our data for training. And secondly, so you notice with this sort of splits, we only ever see we only get one estimate based on our validation sample. Okay, and only get one estimate of prediction. Error, because we only have we split it once, and then that's all we do. We train and then we validate. So the validation only gets assessed on the 20% that was held out for validation, and then our training never uses the entire data set. Okay, so this is one. So if we have a lot of data, like almost unlimited data, then that might not be an issue, but in practice, the amount of data that we have is often limited. Okay, and so there's extensions to this strategy, which is cross-validation, which can actually overcome both of these two weaknesses. By doing cross-validation, we can use all of the data for training in what we call various folds. And secondly, we can get, for each fold, we will get a separate estimate of prediction error. Okay, so let me get rid of this picture and then let's outline cross-validation procedure. Okay, good. Stream is still on. It's just my my monitoring on the laptop froze for a moment there. Okay, so cross-validation. So better is use some sort of a cross-validation scheme. Okay, so what I'm going to describe here is the classic cross-validation with, okay, so we're going to abbreviate that as CV, okay? Okay, so this is how to do cross-validation with, let's say, capital K folds. Okay, so let's draw a picture of our data. So let's say we have these values. Okay, so we have y, x1 up to xp. Okay, so we have. And what we're going to do is we're going to divide our data into k blocks. Okay, so 2. Okay, so let's call this part folds. So we call these things folds. Okay, so 1 to up to k. Okay, so what we do is we divide. So what this picture is showing is we divide our available data well, I should be specific here. So the available data that we could use for training validation into so what do we call these folds are these blocks of data, so into k roughly equally sized equally sized sets. So these are what we call folds. Okay, and usually we want to do this randomly, but once we divide it, then we can fix the folds for that for the process of assessment. Okay, usually randomly. Okay, so once we divide it, we fix it for the training and validation process on these k folds. Right, so what we do then is, well, we basically do this process. So we kind of talked about this, once we train validation, we just, instead of doing it once, we do it k times. Okay, so it's pretty intuitive. So if you're working on fold 1, then you treat this block as your validation sample, and you train your model on everything else. Okay, so for CV fold little k, let's say, you will use data in fold k as validation and train on the rest of the data. Okay, and so again, after we do that, so essentially we're repeating the process capital K times, and so what that ends up giving us is capital K different estimates of our prediction error. So in that sense, so as we cycle through each of these folds, what we're leaving, so it overcomes these two weaknesses that we encounter. We have limited data because eventually we'll have used all the data at some point for fitting models, and we'll also have at some point evaluated the model as validation data for use as validation data, everything in our data sets at one point or another through the process. Okay, and so let's continue the discussion. So thus, to estimate the prediction error, okay, so for a given model, so what this procedure gives us is then we fit it, so we fit it k times, capital K times, each time treating the data in fold, okay, so 1, 2, up to k as validation. that gives us then is we get capital K estimates of prediction error. For that particular for that particular model. Okay, and so for example, if we were to use using RMSE, we would get okay, so we have K calculations of RMSE, so RMSE 1 for fold 1, RMSE for fold 2, up to RMSE for fold cap K. All right, and so you have K different estimates. Now we don't have just a single estimate. We can give ourselves perhaps a more stable estimate by averaging these. Okay, and so we can take the average. Okay, so the average would be 1 over K. So add up little k from 1 to cap K of these. Okay, so take the average. As and our estimate of the root mean squared prediction error. Okay, so I'll put the p here as the estimate of that if we were to then apply the model on new training data. Okay, so remember that is the test set. Okay, so that's the basic idea of cross-validation. Pretty intuitive. So I do want to show you a quick demo before we close for today. So I'm going to switch over to the computer, and we will rejoin you in just a moment. Okay, so I just want to demo this idea of doing cross-validation. So this is just going to be a small example. Just to illustrate how to do this. Okay, and then next class I'm going to talk a little bit more about stochastic variable selection procedures and get into a larger data set. But for now, let's just revisit our coffee data. Okay, so I'm going to load that up here, and okay, I'm going to do the usual setup as we did. Let's set up those indicators ourselves, and then ditch the categorical. Okay, and I'm going to call n here, our cap n here, the total number of observations that we have for the purpose of training and validation. Okay, so suppose this is what we have to work with, is the observations in the sample. So I'm going to call that n. Now, so let's first apply the simplest idea of simply taking all the observations we have and dividing it into a set for training and a set for validation. So here's some R code to show you how to do that. Okay, I'm just going to set a seed here so that you can replicate my results. All right, so Okay, so what I want to do then is I want to randomly select 80%, say, of my data as my training sample. So what I'm going to do is I'm going to take so what this command does, sample, is it draws a random sample from these numbers. Okay, so for all my data indices from 1 to n, I want to choose 80% of them, and I'm just rounding it off to the nearest integer. To be explicit, we want to sample without replacement. So let's make that explicit here. Replace equals false. Okay, so I'll choose 80% of these indices and I'll return a vector with them. Okay, so you can see there's 119 in terms of number of observations. Okay, so let's select the observations we're going to use for training. Okay, so if I look at the observations in here, there's 895 of them, which is 80% of the training sample, and you can see you can see that these are just the random observation numbers chosen from the data set. Okay, and so then once I have the indices, I can easily construct a train set and a test set. So basically the train set is simply to select the rows that are in the set of training indices. So that's how I can select the rows. So that's my train set. And then the remainder are going to be used for well, I should be a little clearer here. I can call this the validation set. Okay, and then I'll put the rest in the validation set. Okay, and so you can see over on the right, I have the corresponding dimensions of 895 observations in the train set and 224 in the validation set, and they represent a random split of 80% and 20%. Okay, so now let's follow what we talked about today. So I'm going to try a few different models. Okay, so I've called these models M1, M2, and M3. So for example, they include different sets of predictors. Okay, so based on the context of the problem, I'm using flavor as the response, and then what's different between M1, M2, and M3 is I'm using, as you can see, different sets of predictors. Okay, so the M2 model is a bit larger than the other two. It has 9 predictors, and then here's a simpler model with just 5, and M3 only has 2 predictors. Okay, so this is how we can use this training validation idea to assess how these 3 models are going to perform in terms of root mean squared error on the validation set. Okay, so what I'm going to do is I'm going to fit these models using the training set. Okay, so I'm going to do that, and then I'm going to use what we learned when we talked about predicting with linear models. Is we can use our predict command. So use the fitted model and then apply the new data. Okay, so I'm going to change all these to validation set so the names are clear. Okay, so I'm going to generate to predictions. As you can see, these are just all the predicted values for the indices in the test set. In the validation set. Okay, so once I have the predictions for these 224 observations that were not used to fit my model, I can now compute various metrics. So I can compute the root mean squared error, for example, on this validation set. So I basically just type in the formula. Test set with the variable flavor is the actual yi, and then I'm going to subtract off what I predicted. So that's yi hat for these 224 observations. I'm going to square them. Okay, so that's the squared errors. Take the average of that, so that's the mean squared error, and then take the square root of that. That gives me the root mean squared error. Okay, so I can calculate that. And of course, I forgot to change this to validation set, so let me do that. And we will have our calculation of the root mean squared error on the on the validation set. Okay, so it's like 0.157. So remember, the interpretation is because I did not use the validation sets for fitting the model. If I were to apply the model now to do prediction on brand new data that we don't even have right now, this would be one guess of how well this particular model, M1, would perform on new test data. Okay, so let's do the same for these other two suggested models. So we're going to compare the M1, M2, M3. Okay, so remember, we can fit as many models as we like on our trained data and then assess each of them on the validation. So let's do that. So it's M2. Let's generate a set of predictions using this fitted model and then calculate its root mean squared error on the validation. So this one, model 2, is actually lower, is 0.142. And then finally, I have this simplest model with just 2 predictors. Okay, so let's try that as well and generate a third set of predictions. And the root mean squared error on validation for this model is the highest of the 3 at 0.161. Okay, so as mentioned, we just do the simple train and validation split. We only get one estimate of these root mean squared errors. Okay, so what we can do as an extension is to do cross validation. Okay, so let's do k-fold cross validation, and just for sake of illustration, I'm going to do k folds. Okay, we'll talk a little bit more about how to choose these folds when we pick up on this discussion next time. For now, let's just use 5 folds. Now, what I need to do is I need to now randomly divide my training and validation data. So based on what we have in terms of the indices. So I have 1119 observations. So I randomly want to allocate 1/5 of them approximately to each fold. Okay, so what I'm going to do is, again, I can use the sample command to do that. Again, I should probably call this validation test set splits. I'll update that before I upload the code. Okay, so what this is going to do, so I'm going to take, so this 2% signs is R's modulo operator. So basically taking each of these and I'm going to divide like mod 5. So I have roughly 1/5 of them are going to be labeled 1s, and another 1/5 are going to be labeled 2, and up to 5. Okay, so that's what accomplished here. Okay, so for example, if I show you this just shows you, this is just the remainder, 1, 2, 3, 4, and then 0, 1, 2, 3, 4. Okay, so I can add 1 so that I get numbers 1 to 5, and then I'm going to randomly arrange them. So I'm going to sample to get a random arrangement of these. Okay, so just to show you, so this is basically you're going to have 1/5 of the data are observation going to be labeled 5, 1/5 going to be labeled 2, and so on. Okay, and so I'm going to use this as my random division of the 5 folds in my data. Okay, and I'm gonna set up some RMSE vectors, which I'm going to calculate for each fold. So what I'm going to do is how I'm going to use this vector is, well, for each time I go through, okay, I'm going to change all the test validations after, so it's cleared and matches the framework we've been talking about. So what I'm going to do is for validation, I'm going to use all the that 1/5 of the data, which have the index corresponding to the value k. I'm going to use a for loop to go through these 5 times. Okay, so on the first time, I'm going to choose all the random indices that are 1, so it's 1/5 of the data, and use that as validation, and use the rest, so that's the ones that are not equal, as training. So I'm going to go through these, and then each time I go through, I'm going to do exactly the same thing. I'm going to fit the model on that fold for training, and I'm going to do prediction on that validation set for that fold, and then I'm going to store the RMSE for that validation fold in this RMSE vector. Okay, so all of this is exactly, all of these lines are exactly the same as before. Okay, except we're now going to repeat that using cross validation and do it 5 times. So then every observation will be used at some point for validation, and then the remaining 80% in that fold are used for training. Okay, so therefore we're going to get 5 estimates of our of validation error for each of the 3 models, and we can get a clearer sense of whether these differences we saw in the root mean squared errors are actually, whether these are actually stable. Okay, so we're going to have 5 estimates of root mean squared error validation based on the 5 folds for each of these models. Okay, so I'm going to go ahead and run that code. Okay, so this will do the 5-fold cross validation. And so now I can, for example, I can look at the values. So RMSE1, so these are the RMSEs for my first 5 predictors. Okay, so each of these RMSEs were calculated on that corresponding 1/5 of the data. Okay, so I have 5 estimates now of what might be my model performance if I were to apply it on new data. Okay, I can do the same for the other 2 models. Okay, and so as I outlined on the board, well, we have 5 estimates. We can simply take the average. Okay, so this is my expected model performance then, based on my 5-fold cross validation for what might be my prediction error if I were root mean square prediction error if I were to apply it on brand new data. So we can see whether the trends we observed hold up now that we stabilize our estimate by doing cross validation. So indeed, the first one has model 1 has a larger RMSE than the second one, and the third one has the largest RMSE. So you notice these numbers are a little more stable, and you notice that compared to my based on just the single split, you notice some of the gaps between the models narrowed a little bit, but we do get more confidence that indeed model 2 in this case is the best in terms of its ability to generalize for prediction on potential new data. Okay, so that's how you can do cross-validation. And so I'm going to pause if there are any questions before we call it a day. So when we come back next time, we're going to look at a more complicated example where there's actually a lot of predictors, and look at ways to generate potential models that we can use as part of this cross-validation process. And we're going to also talk about some other practical points when applying cross-validation in practice. Okay, but are there any questions before we call it a day? Can we use a mean absolute value as a metric for comparison? Yeah, certainly we can. So it's just a matter of changing the formula here. For example, if we go back up here, so we do this part again. So this one would be the root mean squared error. Okay, so I can use a different formula. So for example, if I do okay, so I'll take the difference between yi and the yi hat. Okay, so if I want to do mean absolute error, I can take the absolute value of this. Okay, so that's the absolute value of the error, and then I can take the mean of all these, and that would be the mean absolute error. Okay, so we can certainly apply whichever metric we choose. It's just a matter of adjusting the formula that we use here. Okay, so that's a good question. That's how we can implement, for example, mean absolute error. Okay, any other questions before we call it a day? Is MAE the same thing formulaically as the mean absolute deviation? Yeah, I guess that's just a matter of semantics and terminology. For example, we can do. So we do least squares is our usual way of fitting beta. But there's also variants of regression where we can minimize, like take the least absolute. Minimize minimize, for example, the sum of the absolute errors or deviations. Okay, so if you like, you can also try comparing the three models. For example, using mean absolute error as well. And see whether that, for example, that leads to the same conclusion, that M2 is, for example, better than the other two on multiple metrics. That gives us further confidence that it's a good one to use, the best one to use for prediction, for example, out of these three models. Okay, so with that, let's sign off for today, and we're gonna do a bit of a more in-depth demo on Wednesday, and we're gonna start scaling this up, right? So here we only had about 9 predictors. Okay, so we're gonna show you an example where we have over 100 predictors, and we're gonna see some actual illustrations of what happens. For example, when we have overfitting, and so we'll be able to see a more real-life large data sets when we come back next time. And we're also going to talk about some ways of randomly selecting predictors, especially when that can give us a little more flexibility on top of just the deterministic stepwise procedures that we've seen so far. Okay, so stay tuned for that, and we will pick that up on Wednesday.